Community search aims to find a cohesive subgraph from G that contains Q. It has application in medicine areas, including fraud detection, traffic prediction, and product recommendation. We adopt K-core as our complete definition in this paper. As shown in the slide, given a graph G and a cohesiveness parameter K, a K-core is a subgraph of G whose all nodes have a degree of at least K. This slide demonstrates how different K values result in community of varying cohesiveness. Coheness is defined based on K-core. Each node in the graph can be assigned a coheness value representing the maximum K-core to which the node belongs. For example, the red node in the sample graph belongs to 1 core, 2 core, and 3 core, so its coheness value is 3. We can easily derive a lemma. Given the carry node, all nodes in the community containing the carry node have a coheness value at least equal to that of the carry node. As shown in this slide, the red carry node had a coheness of 3, and all nodes in the final community have a coheness value greater than or equal to 3. Next, let's discuss our motivation. Our main research focus is learning-based community search. Existing learning-based community search methods have some shortcomings which inspired our work. Firstly, current methods lack the capture of community-related features. Secondly, these methods are mostly based on the JSON framework, making them difficult to apply to large graphs. Lastly, this method cannot handle scenarios with changing graph structures, as trained models are difficult to apply to new graphs. Based on our motivation, we first proposed a novel neighborhood community vector to capture community cohesive structure-related information. Then, we designed a transformer model based on graph transformer framework to learn this vector and assist in completing online community search. Finally, we extended our method to dynamic graph scenarios. Now let's move on to our method part. This is the overall framework of our approach, which can be divided into 3 main parts. First, the construction of neighborhood community vector. Second, coheness prediction based on graph transformer. And third, community search based on the trained model. To construct a neighborhood community vector, we need to calculate the H-index value of nodes. The H-index was originally used to evaluate researchers' academic output and level. We adopted it because the H-index can, to some extent, reflect the cohesiveness of node neighborhood. A larger H-index implies a more cohesive neighborhood. The calculation of H-index depends on the degree of each node. Based on the H-index, we also introduce higher-order H-index. The first-order H-index depends on the degree. The second-order H-index depends on the first-order H-index, and so on. We can observe that as the order increases, its value approach coheness more closely, or more precisely, it approaches the upper bound of coheness. This is why we consider the information related to cohesive community. After obtaining the H-index value of nodes, we can calculate the neighborhood community vector for each node. To calculate the target node's neighborhood community vector, we first count the coheness distribution of node and its neighbors. As shown in this slide, we counted the coheness distribution of node 7. We counted the H-index distribution of the node 7. We initialize a zero vector with a length of maximum coheness plus 1, where each dimension index value represents the H-index value. For each H-index value counted, we add 1 to the corresponding position in the vector, and finally normalize the vector. In simple terms, this neighborhood community vector represents the H-index distribution of target node's neighborhood. After obtaining the neighborhood community vector, we will calculate a sequence neighborhood community vector based on this vector. The basic idea is that the target node continuously aggregates information from its neighborhood. As shown in this slide, the first vector in the sequence is a neighborhood community vector we obtained above. Then we use the vector obtained by aggregating its one-hop information as the second vector in the sequence, and so on, until the sequence length reaches our set length. If we use matrix multiplication to express it, the feature matrix and the adjacency matrix are continuously multiplied. Next, we use the transformer-based transformer model to process the above sequence and then use predicting coheness as a downstream task. The first part of this slide represents the sequence of neighborhood compute vector, and the second part represents the transformer model. In the third part, we convert the node sequence representation into node representation by an attention fusion mechanism and use coordinates prediction as its downstream task. After completing the training, we can obtain a model for predicting coordinates. Based on the model capable of predicting coordinates, our online search process is as follows. First, we find the candidate subgraph from the query node using BFS. Then, we use the model to predicting the coordinates of query node and candidate nodes. Based on the lemma mentioned at the beginning, the coordinates of candidate node is greater than or equal to the coordinates of query node. We then filter out the community. Next, we extended the above search process to dynamic scenarios, addressing the three types of changes in graph structure: node deletion, insertion, or both. Changes in graph structure will cause changes in node h-index. We first update the h-index of node, and then calculate the neighborhood compute vector. In the search phase, we still first find the candidate subgraph based on the query node, and then use the model trend before the graph structure change to directly predict the coordinates of query node and candidate nodes. And finally, filter out the community based on coordinates. The next part is the experiment part. First, we evaluate a total of 8 methods, including our method, on 7 datasets. We found that due to the limitation of Yuxiang framework adopted by these baselines, most of them encounter out-of-memory problem on large-scale dataset. In terms of effectiveness, our method improved by an average of 20.6% compared to baselines on all datasets. In terms of efficiency, our method is faster than most baselines. And next is a visualization of search results of transformer and QDGN on Crowd datasets. Yellow nodes represent query node. Purple nodes represent nodes that both methods can find. Red nodes represent nodes that only transformer can find. Blue nodes represent nodes that only QDGN can find. And node with bound edges represents the ground truth. It can be seen that our method covers more ground truth nodes compared to QDGN. To verify the effectiveness of neighborhood compute vector for community search, we also conducted experiments using 3 additional different feature vectors: one-hot, random encoding, and positional encoding. The experimental results show that our method is effective for community search tasks. Then we explore 3 parameters that might affect the model performance. First is the order n of h-index used. We found that higher order h-index do not significantly improve performance, but introduce additional time overhead. Then we explore the influence of neighborhood compute vector sync length, L, and found that as the captured neighborhood range increases, the search effect improves, but additional training time is needed. Finally, we explore the influence of search range parameter R. The search time is positively correlated with search range. This is because we need to predict coordinates for more candidates. Lastly, we have experiments related to the dynamic graphs. Some preparation is needed before the experiment. We divided the initial graph G into different proportions using 3 reduction ratio: 10%, 20%, 30%. This divided the original graph into 2 parts, one for training and other for update nodes. Based on the original graph G and the graphs with different reduction ratio, G1, G2, G3 in this slide, we can simulate scenarios of node deletion, insertion, or both. First is the case of node insertion. We train transformer as on subgraphs with 3 different reduction ratio, then use this transformer directly to perform community search on G. From the experiment results, we found that with a moderate amount of node insertion, using the transformer model train without updates is still effective. Next, we analyze experiments on node deletion. The results show that with appropriate node deletion using transformer model train without updates has some effect. Finally, we have the case that includes both insertion and deletion. The experiment results show that under a certain degree of graph structure change, it is feasible to directly use this formal model trained without updates to complete community search. In conclusion, let's summarize our work. We first proposed that neighborhood community vectors are more beneficial for completing community search tasks. Then we designed a community search method based on graph transformer. Finally, we extended the search task to dynamic scenarios. In future work, we will consider exploring community search on more complex graphs, such as heterogeneous graph. That's all. Thank you, everyone. If you have any questions, please feel free to contact us by email.